Hello everyone. In this video we're going to explore sum and difference identities for sine and tangent. As you recall, in our previous video lecture we went over the sum and difference identities for cosine as listed here, and as I mentioned last time, these are extremely important because we're going to use them to draw, derive the identities for sine and tangent as well, especially the first one, the cosine of a minus b, or the cosine of a difference. So let's go ahead and use these to firstly derive the identity for sine of a plus b. We're going to be using these co-function identities here, which we also went over in our previous video, and that was basically setting up for their usage in this video. And we'll also be using this cosine of a difference identity to come up with the identity for sine of a plus b. So using this co-function identity right here, we know that if you have the sine of an angle, that's the cosine of pi over 2 minus that angle. So now if you consider this a plus b here playing the role of theta in this equation or in this identity, we end up with sine of a plus b equals cosine of pi over 2 minus whatever the angle is, which in this case is a plus b. So we get cosine of pi over 2 minus quantity a plus b. Now if we do a little bit of arithmetic here and distribute that negative sign, we end up with pi over 2 minus a minus b. We can go ahead and group those two because we know cosine of pi over 2 will end up being a nice simple sine of the angle. So now if we apply the difference identity for cosine to this expression, so we have cosine of pi over 2 minus a, quantity pi over 2 minus a minus b. So in this case, all of pi over 2 minus a will play the role of this original a, and b will just be the same as or the original b. So we end up with the cosine of the first angle, which is pi over 2 minus a, times the cosine of the second, which is b, plus the sine of the first angle, which is pi over 2 minus a, times the sine of the second angle, which is b. So we know that cosine of pi over 2 minus a is the same as sine of a. So that's where this sine of a comes from. And we have cosine b just carrying, and we know that sine of pi over 2 minus a, just like right here, this co-function identity is going to just be cosine of a. So we replace sine of pi over 2 minus a with cosine a, and sine of b will carry. And there we have the identity for sine of a plus b. So it's going to be sine a cosine b plus cosine a sine b. Now notice that unlike the cosine identity where the minus here corresponded to a plus there, with the sine identity for a sum, the plus will correspond to a plus. So we don't have the situation that we had with cosine. Now, once we have the sum identity, obtaining the difference identity will be very easy. If you recall, once you have established a fact in mathematics by proving it, then you can use it from that point forward with no problem in any other situation. So we're going to use this identity we just established right away. So what we'll do is we'll take sine of a minus b and we'll turn a minus b into a sum in this clever manner. We can always write a minus b as a plus negative b. Remember, any sum can be written as a difference, and any difference can be written as a sum, as we did in this case. So now applying the sine of a plus b formula, we get sine of the first cosine of the second plus cosine of the first, sine of the second. Now, if you recall, cosine is an even function, so cosine of negative b is just going to be the same as cosine of b. And sine is an odd function, so sine of negative b is going to be the opposite of sine of b. So that's where this positive times that negative, which results from this becoming negative sine of b, will give us this negative here. So we get minus cosine a cosine sine b. And there is the identity for sine of a minus b. We'll summarize it nicely on the next page. So we have sine of a plus b equals sine a cosine b plus cosine a sine b. Sometimes people prefer to write this as sine b cosine a so that you have sine, cosine, sine, cosine. That's fine too. In fact, I'll use it in that way soon. And sine of a minus b equals sine a cosine b minus cosine a sine b. And again, notice that a plus here corresponds to a plus here, and a minus here corresponds to a minus here. So that basically establishes the sum and difference identities for sine. Now we can go ahead and use both the sum identity for sine and the sum identity for cosine to go ahead and derive an identity for tangent of a plus b. So just replacing sine of a plus b with what it's equivalent with, which is sine a cosine b plus sine b cosine a, and also replacing cosine of a plus b with what it's equivalent to, which is cosine a cosine b minus sine a sine b. Now we notice here that everything is in terms of sines and cosines. Since we're trying to come up with an identity for tangent, wouldn't it be nice if we had some tangents instead of sines and cosines? Of course it would, right? So what we'll do is we notice that if we take like the first term, if you just focus on the first term, you'll be able to come up with what you need to divide the top and bottom of this fraction by. To get a tangent out of sine a, we would have to divide it by cosine a, right? But notice that that would leave this cosine here, which we would not want if we just want to get a simple tangent. So what we'll do is we'll go ahead and divide by cosine a to get the tangent there, and then cosine b to go ahead and cancel that out. So we'll go ahead and divide the top and bottom of this fraction by that expression, cosine a cosine b. Now, of course, we can split it up, so we get sine a cosine b over cosine a cosine b plus sine b cosine a over cosine a cosine b. And don't forget, we're doing the same to the denominator, so we end up with cosine a cosine b over cosine a cosine b minus sine a sine b over cosine a cosine b. Now we notice here that this sine a over cosine a will give us tangent a, and notice that the cosine b's cancel out. Plus, on this side, notice that this time the cosine a's will cancel out, and we're left with sine b over cosine b, which is of course tan b, tangent b. Downstairs, notice these two expressions cancel out completely, leaving us 1 minus sine a over cosine a will give us the tangent a here, and sine b over cosine b will give us the tangent b there. So we get this nice expression for the tangent of a plus b, which is tan a plus tan b over 1 minus tan a times tan b, which is also really nice because we have only tangents in the expression. Now, once we have the tangent of a plus b identity, we can use it right away, just like we did in the previous screen for sine, to establish an identity for sine of a minus b. So again, we'll go ahead and write sine a minus b as a plus negative b, so that we can go ahead and use the sum identity which we just established. So we get tangent of the first angle plus tangent of the second angle, which in this case is negative b, over 1 minus tangent of the first angle times tangent of the second angle. Now, if you recall, the only even trigonometric functions were cosine and secant. All other trigonometric functions were odd. That means tangent of negative b, given that tangent is an odd function, is going to be minus tangent b. So that's why this plus turns into a minus. So we're replacing tangent of negative b basically with negative tangent b. And we're doing the same down here. So this minus this time, and that minus that results from that conversion will turn into a plus. So for tangent of a minus b, we get tangent a minus tangent b over 1 plus tangent a times tangent b. So now we have established all the identities for sum and difference of these trig functions that are the main ones: sine, cosine, and tangent. So there we have them all. So for cosine, we have that. There's the cosine of a sum, sine of a sum, sine of a sum, sine of a difference, tangent of a sum, and tangent of a difference. These are identities you're going to want to both understand as well as know by heart, because you'll be applying these a lot, and you don't want to have to run to a piece of paper every time you want to apply one of these identities. So make sure you have absorbed all these that we have discussed so far before you proceed. So let's go ahead and look at some applications of all these formulas and identities that we just found. In this case, we want to find the exact value for the sine of 165. As we discovered in the previous video, a calculator won't help us with that at all, because if you type that into a calculator, such as, for example, Desmos, you'll see that after making sure that it's in degree mode, you'll go ahead and type in sine of 165, and of course we end up with something that is not exact. So we're going to go ahead and use one of our identities, which is the whole point of this exercise. And if we bring up the unit circle, let me bring that up for you. Okay, so here we have the unit circle, and think about a couple of values on the unit circle that you can use to rewrite 165 degrees as a sum, so that those values are easy to obtain. You can see, giving you a minute to think about it, but I think you agree that if we take 120 and 45, that should be a good combination there. So we'll go ahead and rewrite sine of 165 as the sine of 120 degrees plus 45 degrees. So now we go ahead and apply the sum identity for sine, which we know is sine of the first angle times the cosine of the second angle plus sine of the second angle times the cosine of the first angle. All right, so sine of 120 degrees, of course, is the y value. So we know, again, if you only memorize the values for the first quadrant, you'll be able to quickly do a sketch and know the values for all the other related angles to those first quadrant angles, which we should know by heart. So we know that sine of 120 is square root of 3 over 2 times the cosine of 45, which we know is square root of 2 over 2, plus sine of 45, which we know is also square root of 2 over 2, times the cosine of 120, which we know is negative 1/2 because it falls in the second quadrant. Okay, so now we're going to get square root of 6 over 4 minus square root of 2 over 4, which we can of course present in a nicer way by combining those two like fractions and write the answer as square root of 6 minus square root of 2 over 4. So that's one quick application of the sum identity for sines. Okay, so here we have an expression we want to evaluate involving tangent, and we're going to try to use the same kind of trick to try to write negative 7 pi over 12 in a more familiar fashion. But if I could deal with 7 pi over 12 instead of negative 7 pi over 12, that would be easier. So the first thing we'll go ahead and do is recall that the tangent of negative x equals negative tangent x. Remember that tangent is an odd function, so that's why it behaves that way. So we'll go ahead and rewrite this as negative tangent of 7 pi over 12. Remember, this is going to be one of those things that will cause a lot of people errors, so don't forget this negative sign. We're going to keep carrying it in each step. So the first thing we'll do in each step is write that. So now we'll see if we can write 7 pi over 12 using angles that are more familiar to us. If you recall from our previous video, we already did this for cosine, and 3 pi plus 4 pi instead of 7 pi seems to work out well. So notice we end up with negative tangent of 3 pi over 12 will give us pi over 4, and 4 pi over 12 will give us pi over 3. So now we can go ahead and use the tangent of a sum formula. So we know that that equals tangent A plus tangent B over 1 minus tangent A times tangent B. So applying that formula and making sure we don't drop the negative, we end up with tangent of the first angle, which is pi over 4, plus tangent of the second angle, which is pi over 3, over 1 minus tangent of the first angle, pi over 4, times the tangent of the second angle, pi over 3. So notice pi over 4, as we know, is just 180 degrees over 4, or 45 degrees. Pi over 3 is just 180 over 3, or 60 degrees. So for this, we can actually go back to our triangles for once instead of the unit circle, which we could, of course, but let's just remember these two. So we have 45, 45, 90. This is our reference 45, 45, 90, which we know has sides 1, 1, square root of 2. And for the reference 30, 60, 90, we know we have sides 1 opposite the 30, 2 opposite the 90, square root of 3 opposite the 60. So from this figure, you can tell that the tangent of pi over 4, which is the same as the tangent of 45 degrees, will be 1 over 1, opposite over adjacent. And for 60, we can see it'll be square root of 3 over 1, opposite over adjacent. So here, let's not drop the negative. We end up with tangent of pi over 4, which is just 1 over 1, we said is 1, plus tangent of pi over 3, which we just mentioned, is square root of 3, Down below we get 1 minus tangent of power 4, which is 1 again, times tangent of power 3, which is square root of 3. So we have negative, let me make that a bit shorter, 1 plus square root of 3 over 1 minus square root of 3. This kind of expression, of course, we don't consider simplified until we have no more radicals in the denominator. So we'll go ahead and rationalize the denominator by 1 plus square root of 3, and we'll do the same on the top, of course. So we end up with negative 1 plus square root of 3 squared over 1 minus radical 3 times 1 plus radical 3. To handle this expression, which is the square of a sum, we'll need to use this formula. F plus L squared equals first squared plus 2 times first times last plus last squared. To handle the denominator, which is a product of two conjugates, of course we'll use the product of conjugates formula, which, as we know, when you multiply two conjugates like that, you end up with the difference of their squares. So for the top, we have the negative, which we carry. The top becomes 1 squared, which is 1, plus 2 times 1 times radical 3, which is just 2 radical 3, plus square root of 3 squared, which is 3. Down below we have 1 squared, which is 1, minus square root of 3 squared, which is 3. So keep that negative. So on the top we have 4 plus 2 radical 3. Down below we have negative 2. So of course the two negatives are going to cancel out and just leave us a positive. So basically we have 4 plus 2 radical 3 over 2. If we split that up, we get 4 over 2, which is 2, plus 2 radical 3 over 2, which is radical 3. So that's how we're going to leave the final answer. Nicely simplified. All right, so be sure that you can handle something like that on your own before we proceed. Of course, before we leave this problem, go ahead and notice that if we calculate the tangent of negative 7 pi over 12, okay, and this is where you have to be extremely careful, because if you recall, for the last problem we had gone into degree mode, so we have to change back the radians. So here we have the tangent of negative 7 pi over 12, and now if we calculate 2 plus the square root of 3, of course we'll get the same value. So, but this wouldn't have helped us when we're supposed to find an exact value, so there's no getting around being able to do this kind of work. And after all, it's that kind of work which makes you a scientist or a mathematician, not just plugging into a calculator, which is not of much value as far as pardon me there, as far as learning mathematics is concerned. Then you just become a data entry person, which is not what you want to be doing for yourself here. Okay, so that's that. So we'll move on to another problem now. Okay, here is a problem that's going to test our familiarity with the identities that we learned today. And of course, I'm pretty sure you can recognize that and do this problem. So try it on your own before you come to see the rest of this video. All right, so I'm sure you recognize that as being in the form tan A plus tan B over 1 minus tan A tan B. And of course, if you remember, that's the same as tangent of A plus B. So we should be able to write this as the tangent of 77 degrees plus 43 degrees, which is the tangent of 70 as 40 gives us 110, 7 and 3 is 10, so 120 degrees. So all we have to do is find the tangent of 120 degrees. Now, when we draw a unit circle, we know that 120 is right here, so we know it's related to 60. Of course, we have the values for 60 memorized as 1/2 square root of 3 over 2. So we know the value here of the cosine will be the opposite, but the sine, the y value, will be the same. So negative 1/2 and square root of 3 over 2 are going to be the values we're going to be using. So of course we know tangent is sine over cosine. And for sine of 120 degrees, we have the y value at the point which we designated here. So it's going to be square root of 3 over 2 over the cosine, which is going to be negative 1/2. So if you recall, we have the nice trick that if you have one fraction over the other, it's going to be the outer product over the inner product. So we notice that the overall sign is going to be negative. We'll take care of that so we don't forget it. And then we have 2 radical 3, that's the outer product, over this product, over the inner product, which is 2. And of course, we can cancel out the 2's and we end up with negative radical 3. So that's how you would handle a problem like that. All right. So that's for that one. Let's move on to another. All right, so here we're going to go ahead and use identities to write this just as a function of the variable w alone. So of course, we know that we can use our tangent of a plus b formula here, which we know is tangent a plus tangent b over 1 minus tangent a tangent b. By all means, pause the video and see if you can do this on your own. You should be able to, then come back. All right, so we'll come back. So here we get tangent of 45 degrees, which is the first angle, plus tangent of the second angle, which is w, over 1 minus tangent of 45 degrees times the tangent of w. Now, we've seen the tangent of 45 degrees a few times already. It's one of those you definitely want to know. We know that's 1. So we get 1 plus tangent of w over 1 minus. We know again tangent of 45 is 1 times tangent of w. So we just get tangent of w. And that's it. We've written it as a function of w alone. We don't have any angles in there. We should be good to go. Here we're doing a similar problem with sine. See if you can get it and then come back. All right, so we know that this is in the form of sine of a plus b, which as we know is sine a cosine b plus sine b cosine a. I always recommend that if you're going to use a formula, write it down without any modification first, then substitute. That completely minimizes your chances of making a mistake. So of course here what plays the role of A is pi over 6, and what plays the role of B is x, right? So we're going to end up with sine pi over 6 cosine x, that's cosine of the second angle, or B, plus sine x times cosine of the first angle, which were pi over 6, or which was rather. Okay, so pi over 6 we know is basically a 30-degree angle. We can either go to the unit circle or we can go to a triangle. You know, most of the time we'll just go to our unit circle. We know pi over 6 is right around there, and we know that the values for it are going to be square root of 3 over 2 and 1/2. So sine is the y value, of course, so we get 1/2 cosine x plus, let me go ahead and take care of the constant first. Cosine of pi over 6 is the x value, so it's going to be square root of 3 over 2 sine x. Now those are, you know, like fractions because they have the same denominator, so we'll just go ahead and combine the numerators. So we have cosine x plus square root of 3 sine x over 2. And we are pretty much done with that. Notice no angle measurements was desired in the answer, and we don't have that. We just have a function of x. All right, so make sure you can whip that up on your own before we move on. All right, so in this problem we have two quadrant 1 angles S and T, and we're trying to find sine of S plus T and tangent of S plus T, and also the quadrant in which S plus T resides. And all we're given is the cosine of the first angle S, which is 3/5, and the cosine of the second angle, which is T, which is 8 over 17. So before we actually start to do anything, we need to know what we're going to actually have to find first. So let's go ahead and write down those two formulas. So we know that sine of S plus T is equal to sine S cosine T plus sine T cosine S. And we know that tangent of S plus T is equal to tangent S plus tangent T over 1 minus sine S, tangent S tangent T. All right, so basically we are going to need the, we have the cosine of S, but we can see that we're going to need the sine as well. We know the cosine of T, but we can see we're going to need the sine of T as well. And of course, if we have both the sine and cosine of each of those angles, we also have the tangent. So the first thing we'll need to do is go ahead and find the sine of S and the sine of T, recognizing the fact that S and T are first quadrant angles. So the easiest way to get that is just with a quick diagram, and I'm just going to work with S first. So cosine of S equals 3/5 in the first quadrant. So if I just go ahead and construct a triangle. I'm going to have S here, and I know the adjacent side is 3 and that the hypotenuse is 5. Now you probably recognize this as a 3, 4, 5 triangle, but if you don't, you can just call this side y and just use the Pythagorean theorem. So we have 3 squared plus y squared equals 5 squared. So we get y squared equals 25 minus 9, which is 16. So y in this case is going to be positive 4. So we know that this is going to be 4. Of course, you should recognize a 3, 4, 5 Pythagorean triple. All right. So from this picture, we can see that the sine of S, which we're looking for, is going to be opposite over hypotenuse. So it's going to be 4/5. All right. We'll do another diagram, and we'll go ahead and use this next diagram to go ahead and find the sine of t. So we know that cosine of t is 8/17. This program, these digital whiteboards are very touchy. So we want to find the sine of t, so we're going to construct a triangle based on the fact that t is a first quadrant angle and its cosine is 8/17. So this time we know that the adjacent side is 8 and the hypotenuse is 17. This you should recognize as well. This is another famous Pythagorean triple, which is 8, 15, 17. But again, if you don't, you can always call that y and just go 8 squared plus y squared equals 17 squared. So 64 plus y squared equals 289. Let me double check that. So we're doing 17 squared. I believe that's 289. Let me go ahead and clear these. So 17 squared. Yes, 289. So we get y squared equals 289 minus 64. So y squared equals 225. And we know that y is going to end up being the positive square root of 225 because it's in the first quadrant and the y values are positive here. So we get positive 15. So now from this figure, we can tell that the sine of t is going to be opposite, which is, we just found out, is 15 over the hypotenuse, which is 17. All right, so we should be ready to go to work now. So for sine of s plus t, we're going to get right here sine s, which we know is 4/5, times cosine of t, which we are given, which is 8/17, plus sine of t, which we have found here to be 15/17, times cosine of s, which was given. All right, so we get 32 plus 45, And we can see both of those denominators are going to be the same, and they're going to be 85. So over 85, and we end up with 77 over 85. So this should take care of the part A of our question. For part B, we need to find tangent of s plus t. Which, using the formula, is going to be the tangent of s. Now, we have actually a nice graphic of s right here. So tangent is opposite over adjacent. So it's going to be 4/3 plus the tangent of t, which we can see from the picture, will be 15 over 8. Over, let me actually move this down a bit so our expression looks proper. Over 1 minus tangent of s, which we found to be 4/3, times tangent of t, which we found to be 15 over 8. Okay, so let me see here. We can go ahead and reduce a little bit to make life easier. That's going to leave us a 2 here. So we have So we have 4/3 plus 15 over 8 over 1. By the way, we have more simplification we can do here. Those two leave me 5. So 1 minus 5 over 2. Let me go ahead and throw 1 under that. The easiest way to simplify a fraction like that, which is called a complex fraction, is go ahead and multiply the top and bottom by the LCD of all the denominators. Notice the LCD for all of them will just be 24, right? So we're gonna do that. We're gonna go ahead and multiply 24 and distribute. So basically each term on top and the bottom is going to get multiplied by 24. And we notice that we have some cancellations here. These two will leave us 8. Those two will leave us 3. And these two will leave us 12. So let's see what we have now. So we have 32 minus 40, plus actually 45 over 24 minus 12 times 5, which is 60. So we end up with 77 over 24 minus 60, which is negative 36. So we can just write that as negative 77 over 36 for the nicest form. All right, so we did just complete part B. So the only part left is C, which is going to require a little bit of thinking, because remember, they want to know which quadrant s plus t falls into. Remember, we don't know the angles s or t exactly, but we know the sine of the angle and we know the tangent of the angle. Now, if you remember, tangent of s plus t is equal to sine of s plus t over cosine of s plus t, right? So we have that the tangent is negative, right? And we know that the sine is positive. And how could that happen? Notice that if the sine is positive and the tangent is negative, right? That can only happen if the cosine of s plus t is negative, correct? Think about that for a minute. Because if that's not the case, how could the tangent be negative? Because tangent, after all, is sine over cosine, right? So if the tangent is ending up negative, and we know that the sine is positive, that forces the cosine to be negative. So in what quadrant are the sine and cosine both negative? And of course, you know that is the sine positive and the cosine negative, and clearly that's going to have to be quadrant 2. I was pointing to the right quadrant, but I misspoke. So that's where the sine is positive and the cosine is negative. So this is going to have to be a quadrant 2 angle. All right, so that's a nice problem. It requires some skills from pretty much the entire semester. So make sure that you know how to handle something like this before we move on. Okay, so we're going to now prove a few identities, and then we can pretty much call it the day. All right, so in this first problem, we're going to be proving that sine of 2x equals 2 sine x cosine x. So if we just start with sine of 2x, so here's the proof. The game plan will be that we'll start with the left side and work our way to the right side. At any point that you feel like, oh, I've got this, then please pause the video, do it on your own. That's how you learn, okay? So this is going to be, as you know, sine of x plus x. If you remember, we used this trick for cosine of 2x in the last video, and we ended up with 3 forms of that. We won't be as lucky in this one. We're only going to get 1 form, but this is going to be an extremely important form which you'll use a lot in this class and also when you move on to calculus. So here we're going to go ahead and apply the sine of a plus b identity, which is, as you know, sine a cosine b plus sine b cosine a. So applying that, and remember a and b are going to be both the same, namely x. So we get sine x cosine x plus, yet again, sine x cosine x. So notice we end up with 2 sine x cosine x. And there you have the identity that you were trying to verify indeed verified. And we started with the left side and through some legal steps ended up with the right side. This is the proper way to present your verifications of identities, your proofs that identities are correct. So be consistent with your presentation. And of course, now we can say QED because we are finished. Okay, so next we're going to try to prove this identity. I definitely invite you to try it on your own first before you come back. All right, so looks like we have more to work with on the left side, so let's go ahead and start on the left side. So we have cosine of alpha plus beta over sine alpha sine beta, and let's go ahead and apply the identity that we know for cosine of alpha plus beta, and that's basically the way you approach most of these identities. You do want to keep an eye on the right side that you're trying to get to and make sure you get there, but mainly you do what's available. So that's basically the strategy. Here I notice, okay, what can I do? Well, I know what the cosine of alpha plus beta is, so why don't I go ahead and expand it and see what I end up with. And of course, that's a sum identity for cosine, so it's going to be cosine alpha cosine beta minus sine alpha sine beta over, we have sine alpha sine beta, which we're just carrying it. All right, so next I look at this and I say to myself, what else can I do? Well, I have a combined fraction, so maybe I can split it up. Not only that, but I noticed that, hey, that would end up with a cosine over sine situation, which should be helpful for me. So next we'll go ahead and do that. We'll split that up, so we get cosine alpha cosine beta over sine alpha sine beta minus sine alpha sine beta over sine alpha sine beta. And now I notice that cosine alpha over sine alpha, that's looking like where I want to get to. So I'll go ahead and write that as we know, cotangent of alpha. And we know that cosine beta over sine beta is also cotangent of beta minus, and of course this looks really nice, everything cancels out and we're left with 1. And we take a look, and that's exactly where we were supposed to end up. So these are not difficult, but you do have to know your basic identities, and you definitely have to remember your algebra. So that's it for that one, and we're done. So make sure that you can do that on your own without looking before we proceed. Just practicing these, of course you'll do much more practice once you do your homework or whatever assignment you have, but just being able to do that, even if you've seen it, just being able to do it on your own shows that you're on the right track. All right, so here's another identity for us to verify. Now when I look at this, I could go from left to right or right to left, but I know that usually it's easier to go from tangent to sine or cosine than the other way around. Because if you go the other way around, you usually have to pull something out of blue sky to be able to handle it. So this time, let's go ahead and try to go from the right side and end up with the left side. And remember, either direction is perfectly okay. So here, we'll go ahead and start with 1 minus tan x tan y over 1 plus tan x tan y, and we'll go ahead and basically, one of our fundamental strategies for proving identities, if you have anything other than sines and cosines, go ahead and turn them into sines and cosines. So that's what we'll do next. We'll go ahead and write the tangent of x as sine x over cosine x. And we'll do the same for tangent of y. Sine y over cosine y. And we'll do the same downstairs. So 1 plus sine x over cosine x times sine y over cosine y. So of course, another one of those things we've noticed with identities is if something is already combined, break it up. If it's not combined, go ahead and combine it. So let's go ahead and try that. Now, in this case, we can either combine and then do outer over near, which is one strategy for simplifying a complex fraction, or we can use the other trick we've discussed a couple of times, which is really nice, which is to find the least common denominator of the top and the bottom of the complex fraction and just go ahead and multiply that on the top as well as the bottom, and that will clear the fraction. So let's try that instead. Notice that here the LCD is just going to be cosine x cosine y, because you can think of the 1 as 1 over 1, so that's not going to be an issue. And the same downstairs. So what we'll do now is we'll go ahead and multiply the top and bottom of this complex fraction by cosine x cosine y. And remember, that's going to get distributed, so you'll have it once there, you'll have it once here, you'll have it once over here next to the other one, and then we'll have it once here. Of course, notice we're only multiplying it once on the top and once on the bottom. It's because we then distribute that we end up with the expression getting multiplied by all 4 terms. So that's because of distribution. So now let's see what we have left. So we have cosine x cosine y from that first term on the top minus sine x sine y over cosine x cosine y from the first term on the bottom plus, and from the second term we just get sine x sine y. And of course, if you have done what you're supposed to do, which is memorize those identities from earlier, you remember that cosine of a plus b equals, let me write that a little bit further to the left so I can fit it. We have cosine of a plus b equals cosine a cosine b minus sine a sine b, and we have cosine of a minus b, almost the same thing but with the different sign, cosine a cosine b plus sine a sine b. So notice that on the top here we have exactly that kind of an expression, so that's just going to be cosine of x plus y. And downstairs we have an expression exactly looking like that, so that's going to be cosine of x minus y. And that's basically what we were supposed to arrive at, because remember, our strategy was to start on the right side and through some legal steps end up with the left side, which is exactly what we did. So at this point, we are finished with this proof, and we can say QED. All right, so make sure that you understand that, and we'll look at another one. All right, so we have finally arrived at our last problem, and it looks like we can do more with the left side. So let's go ahead and start with the left side exactly as it is. So sine of s minus t over sine t plus cosine of s minus t over cosine t. That is the proper way to write one of these proofs. Sometimes we get lazy and try to do one step at least at the beginning of the proof, but that's not the proper thing to do. So just write one side exactly as it appears. Now, of course, here we have two fractions. You know how it goes with identity proofs. We'll go ahead and see if we can make them one fraction by combining them. So the LCD is sine t cosine t. And of course, to make the first denominator like the common denominator, we're going to have to multiply by cosine t. And we'll have to do the same on the top. And for the second denominator, we'll have to multiply it by sine t. So we'll do the same on the top. Now, generally, if I'm presenting this proof, I'm not going to have all that written because it takes away from the purity of the proof. But of course, I'm doing it here for instructional purposes. Normally, this will happen in our heads, right? So the proof will look nicer that way. But there they are in case you're going to wonder where things come from. So here we end up with cosine t times sine of s minus t plus sine t times cosine of s minus t. All right, so again, we ask ourselves what can be done, and it looks like the only thing we can do is go ahead and expand these two expressions using the identities that we've learned today. So we're going to go ahead and turn sine of s minus t into sine s cosine t minus sine t cosine s, and we'll do the same with cosine of s minus t. And of course, we learned that identity the other day and we reviewed it today. So we'll get cosine s cosine t plus sine s sine t. And that is all over sine t cosine t. All right, so if we go ahead and multiply this out, we'll end up with sine s cosine squared t minus sine t cosine t cosine s plus the next distribution right here will give us sine t cosine t cosine s plus, notice this sine t times that sine t will give us sine squared t. So we get sine s times sine squared t, and then all of that over sine t cosine t. Okay, well, some glimmer of hope is starting to emerge. As you can see, this term, negative sine t cosine s, is exactly the opposite of that term, positive sine t cosine s. So right away, we can go ahead and cancel those. Also notice that this term and that term have a sine s in common that can be factored out. So let's go ahead and try that. So we end up with sine s times cosine squared t plus sine squared t over sine t cosine t. And of course, if we don't recognize anything else in trigonometry, we should recognize this object because of our Pythagorean identity. We know that's 1. So basically, we end up with sine s over sine t cosine t. And that's precisely where we want it to be. So notice you just need to be patient, and you definitely need to brush up on algebra if you haven't done so already. And also you want to make sure you have memorized your fundamental identities that we've learned so far, and you should be fine. So make sure you go over all this stuff and any assignments, and be safe until the next time that we meet.